In this training exercise, we will be discussing the new features and functionality of the regulatory DFIRM database. We will start with a general overview of the datasets to explain the new or updated fields, and then demonstrate how to use the database to interact with the engineering data stored in the tables within it. The data within the regulatory database can benefit users from numerous backgrounds. Whether it be government officials, users from the private sector, or citizens, each can find value in the new features and functionality of the database. Its new design as a relational database will make it easier for communities and homeowners to understand the engineering analysis behind the new or revised FIRMs and regulatory floodplains. Feature classes and tables that have been changed or added include the following. The first dataset we will look at is the flood hazard area. Changes to this feature class include the addition of the study type and zone subtype fields. Study type designates whether the special flood hazard area is high or low risk. Zone subtype further defines the flood zone field. This is determined based on the type of study that was performed. Special flood hazard areas identified by new detailed studies are higher risk than approximate studies. The profile baseline is the next feature class we will look at. It is now a 3D feature class, meaning that in addition to having a latitude and longitude, or x and y value, there are now z and m values associated with each vertex. The z value represents the 1% annual chance flood elevation, and the m value represents the stream stationing. The stream stationing is calculated from the most downstream point or the beginning of the flood study. The L Manning's N table contains information on Manning's N or K roughness coefficients used in the flood risk project to create the FIS report roughness coefficients table, and it is linked to the profile baseline feature by the water name field. The cross-section feature class has also undergone some changes. Under the new guidelines, all cross-sections are shown on the FIRMs, whether they are lettered or not lettered, and they are all labeled with the 1% annual chance flood elevation. This eliminates the need to show base flood elevations, or BFEs, on the FIRMs, which reduces clutter. The cross-sections are also related to the cross-section elevation table by cross-section ID. This new table stores elevations for multiple flood events, including a 1% annual chance plus event. This event is derived by using discharges that include the average predictive error for the regression equation discharge calculation. This provides a buffer of accuracy for the 1% annual chance floodplain to reinforce that these are modeled events and that the floodplain boundary may vary slightly in real-life scenarios. The Station Start feature is a new spatial layer that describes where the detailed study begins. This information can also be found on the profile in the FIS. Now that we've discussed the changes to the datasets, we will demonstrate how to use the datasets within ArcGIS to perform an analysis in a scenario that will simulate real-world implications. For this demonstration, we will be using the standard symbology used on the regulatory FIRM panels. Note that the building footprint layer shown here is a supplemental dataset and is not included in the regulatory database. However, a building footprint dataset is included as an enhanced feature in all non-regulatory databases for risk map projects performed in Alabama. In this scenario, a property owner wants to know if his home is in the special flood hazard area and what the base flood elevation, or BFE, is at his property. He has surveyed his home and the finished floor elevation is 649 feet. We will now use the datasets we discussed at the beginning of the video to help the property owner answer his questions. We will first navigate to the address in question using the building footprint layer and visually verify that the building is inundated by the special flood hazard area. Next, we will do a select by location to double check that our visual verification was accurate. From the selection menu, choose Select by Location. Select features from the special flood hazard areas that intersect the building footprint layer. select the Use Selected Features box and set the spatial selection method for Target Layer drop-down to intersect the Source Layer feature. Click OK. This will highlight any features in the flood hazard area that overlap with the highlighted building. Right-click on the flood hazard area layer and select Open Attribute Table. Click the button Only Show Selected Features. This shows that the building intersects with a zone AE. Next, we will verify that the elevation of the property is correct. To do this, use the ID tool and click on the cross-section upstream of the building. Note that the regulatory elevation is 652.1. Next, click to identify the downstream cross-section. Note that the regulatory elevation is 648.1. This means that the regulatory elevation of the building in question has to have a value between 652.1 and 648.1. To verify this further, we will use the z-values available in the new Profile Baseline feature. Start an editing session on the Profile Baseline. Double-click the Profile Baseline, then open the Edit Sketch Properties window to display the values of the vertices. Select the vertex that is closest to the building. Scroll through the list of vertices until you find the one with the checkbox. Verify the regulatory elevation with the value from the Z field. The same elevation can also be verified on the profile in the FIS. Having all of this data in a spatial format allows you to more efficiently cross-reference multiple data sources, which streamlines the analysis process. This concludes the training video.